aim of the experiment is to plot the transfer curve of BJT and MOSFET. So let us first start with the transfer curve of BJT. BJT stands for bipolar junction transistor. It is a three-terminal device. The three terminals are named as the base, emitter and collector. We have different configurations of transistor. We can have common base configuration, common emitter configuration and common collector configuration. The most frequently encountered transistor configuration is called as common emitter, where the emitter terminal is common to both the input and output junctions. The input terminal is the base terminal and the output terminal is the collector terminal. You can look over here, we have used a SL100 transistor, and when you look at the transistor there will be a notch. The terminal which is closest to the notch is emitter, the one which is closest to emitter is base, and the one which is far away from the notch is the collector terminal. This is the circuit diagram for drawing the transfer curve of a bipolar junction transistor. You can see here the emitter terminal is common to both the input and output junction. So the input junction is between the base and emitter, which is called the base emitter junction, and the output junction is between collector and emitter and is known as the collector emitter junction. The input terminal is the base terminal and the output terminal is the collector terminal. We have connected a voltage supply between the base and emitter denoted as VBB, and similarly you can see a supply voltage connected between the collector and emitter terminals denoted by VCC, that's equal to 12 volts. In addition to that, we also have a base resistance of 2.2 kilo ohm connected to the base and a collector resistance of 1.5 kilo ohm connected to the collector terminal. So this is the basic setup, circuit setup for plotting the transfer curve of BJT. If you look at the graph transfer curve, it is the plot between the input voltage and the output voltage. Means the voltage across the base and emitter is taken as the input over here, and the voltage across the collector emitter terminals is denoted as the output voltage over here. So what is the characteristics? When I say transfer characteristics, what is meant by characteristics? So characteristics is a plot which is going to speak about the behavior of a device. The BJT, we can draw, in case of BJT, we can draw input characteristics and output characteristics. When I say input and output characteristics, we are referring, when I say input characteristics, we are referring to the plot between the input voltage and the input current with output parameter constant. When we are talking about output characteristics, the plot between output voltage and output current with input parameter constant. But in our experiment, we are just going to plot the variation of output voltage with respect to input. We know that a transistor operates in three regions, that is cutoff, active and saturation regions. In cutoff region, both the input and output junctions are reverse biased. In the active region, the input junction, that is the base emitter junction, is forward biased, and the output junction, which is the collector emitter junction, is reverse biased. In case of saturation region, both the input and output junctions are forward biased. In cutoff, as the name suggests, the transistor is cut off because both, you can see here in the circuit diagram, so both these base emitter and collector emitter junctions are reverse biased, as the result of which the transistor is off, and you can see that most of the voltage, supply voltage with little drop is available across the collector emitter terminals. So we will get the maximum voltage, output voltage in the initial stage for lower values of VB, where both the junctions are reverse biased. As VB increases towards a positive value, it increases, the base emitter junction is forward biased, it gets turned on, as a result of which the transistor conducts current, and we can take the amount of collector emitter voltage, that is VCE. You can see it was first maximum because the transistor was cut off. When transistor started operating, current output, we got current output current as IC. So with a drop across 1.5 kilo ohm, you can see slowly the output voltage has now come down. It reduces. That's the active region. And there will be a point where both there is a higher value, for higher values of VBE, our collector emitter voltage will still come down, and that's your saturation region. The current relationship of IE is equal to IC plus IB holds good in case of the transistor operation. In the active region of a common emitter configuration, as I said, the base emitter junction will be forward biased and the collector emitter junction will be reverse biased. The active region of a transistor can be employed for any sort of amplification like voltage amplification, current amplification, or power amplification. This is the observation table of BJT transfer curve. As we have already discussed, the input voltage VBB is varied, and we are looking at how the output varies with respect to input. That is, we are recording the values of VCE voltage. What we observed is, as we go on increasing the input voltage, initially the VCE voltage is constant, that's the cutoff region, so it is a higher value, and then slowly the VCE voltage reduces with further increase in the input voltage, and it reduces and comes down to the saturation region. So this region where you can see for the input higher values of input voltage, we have only 0.02 as the output VCE voltage. This is the saturation voltage, which is also denoted as VCE sat. In the middle region where it slowly gradually reduces from a higher value, this is the active region in which the BJT operates. Now let's discuss the transfer curve of MOSFET. So this is the circuit diagram for MOSFET transfer characteristics, and we can also look at the model graph, which is the transfer curve and the plot between the input voltage and the output voltage. MOSFET is a 3-terminal, unipolar, voltage controlled and high input impedance device. This MOSFET forms an integral part of a variety of electronic circuits as on today. One of the most unique property of MOSFET is that the gate terminal does not draw any measurable current. The 3 terminals of MOSFET are denoted as gate, drain and source terminals. Further, these devices can also be classified into depletion type and enhancement type MOSFET depending on whether they possess a channel in their default state or not. Further, they can also be of P channel or N channel devices, as they have their conduction current due to holes or electrons. The 3 operating regions of MOSFET are cutoff, ohmic region and saturation region. In the cutoff region, MOSFET will be off and there will be no current flow through it. In this region, it behaves like an open switch and is thus used when required to function as electronic switches. When we consider the ohmic or the linear region, this is the region where the current, that is IDS, the drain to source current, increases with an increase in the value of the drain to source voltage, that's VDS. When MOSFETs are made to operate in the ohmic region, they can be used as amplifiers. Now talking about the saturation region, the MOSFET have IDS constant in spite of increase of VDS in this region. And this occurs once VDS exceeds the value of pinch off voltage, that is VP. Under these conditions, the device acts as a closed switch through which a saturated value of IDS flows. You can see here we have connected a voltage between the gate and source terminals denoted as VGS, that is gate to source voltage, and we also have connected a supply voltage of VDD between the drain and source terminals. The source terminal is common to both the input and output junction over here. We also have a substrate terminal which is usually connected to the source. Now we have this drain resistance which is RD, we have taken it to be 1 kilo ohm. Now here also we have to vary the input voltage. This arrow marks denotes the variable voltage. So we will slowly vary the VGS voltage and look and observe at what is the voltage change between the drain and source terminals. So this is the model graph. Now when slowly the VGS, for smaller values of VGS, the VDS is constant, it's a higher value because the MOSFET is in cutoff state. It is off. And then slowly as VGS approaches a given value, you can see that the drain to source voltage reduces. This is your saturation region. And when for minimum value, the further increase in the VGS voltage, we can see minimum value of VDS, and that's your ohmic region. So this is how the transfer curve characteristics of MOSFET is going to vary. If we look at the observation of VDD and VDS, VDD is the input, we will slowly increase the input, and what is that we are measuring at the output? We are measuring the voltage between drain to source terminals. We saw that it is a higher value, constant at 9.7, and slowly it reduces and comes to 0.01 with further increase in the input voltage. Curve of the BJT. This is your bipolar junction transistor with the 3 terminals. You can see the notch here. The adjacent to the notch is emitter. The adjacent terminal to the emitter is base, and the last one is collector here. So we have given a supply here. You can see again we've used a dual power supply here, and we are connecting voltage VBB between the emitter and base terminals. And if you look at the supply voltage, which is around 11.9, that we have connected between the collector and emitter terminals. Now this is your base resistance RB, and this resistance is the collector resistance RC. We will take the drop across the collector and emitter terminals, that is the voltage VCE, so that we are measuring with the help of a multimeter. So now what we are going to see is when we vary the input voltage in steps, how the value across VC is going to change. So this is at 0.0 now, so I'll slowly increase the input voltage which is applied to the input base emitter junction. You can see it is at 0.2, and the voltage across the collector emitter terminals is 11.84. It's not changing. I have still increased the input. So this is your region where the output voltage is fixed because the transistor is in cutoff mode. So whatever is the supply voltage that is appearing with a little drop across the RC resistance, it is appearing across the collector emitter terminals. So that's the cutoff region. And then now you can see the voltage slowly drops. It's dropping. Now this is your active region where with increase in VB we are seeing a decrease in the voltage across collector and emitter, and slowly have increased the input, and you can see now the input is at 1.8, and the collector emitter voltage VCE value is 0.03. Further, if I increase the input beyond 2, this is now not changing, so it's at 0.02, which is your saturation region, and this is the saturation voltage, which is called VE sat. This is the circuit setup for observing the transfer curve of MOSFET. We can look at the MOSFET here. So there are 3 terminals. This is my gate terminal. This is the middle one is the drain terminal, and the last one is the source terminal here. So we have again taken the power supply, which is a dual power supply. So we are connecting the gate to source voltage between the gate and source terminals here. So this is a variable voltage. We are going to vary this voltage, gate to source voltage, and we are going to observe the voltage at the drain to source terminal. So at the drain to source terminals, you can see we have connected the multimeter. So we are going to take the voltage drop across the drain to source terminals. You can see here the fixed power supply of around 9.9 volts, the supply voltage which is connected between the drain and the source terminals, and this is your drain resistance, which is RT. So now I am going to slowly vary the gate to source voltage and observe what is the drop across the drain and source terminals. So I am going to, so it's at 0.0, so I will slowly increase, and you can see the drop across the drain to source terminals is 9.75. We have given a supply of 9.9 with a slight drop across the drain resistance. The value coming is 9.75. Now again I increase slowly, so there is no change. There is no change. Now the input is at 2.1, but still the output voltage VDS is 9.75. Now further, if I increase the input beyond 2, I will slowly increase the input voltage beyond 2, and now you can see the drain to source voltage is slowly decreasing here. Now it's 9.6, 9.39, so it's slowly decreasing. Now the input voltage is at 3.4 volts, that is the gate to source voltage is 3.4, and you can see the drain to source voltage has come down to 0.01. So what we saw is finally that when we slowly increase the input voltage, the drain to source voltage was constant at a high value, it decreased and came to a minimum value here.